This is chapter 10, rotational kinematics. We're going to learn about the velocity, acceleration, and displacement of things that are rotating. Up until now, most of our kinematics has been done with linear motion, and now in this chapter, we'll be talking about rotational motion.
All right, so first, describing rotational motion. A fraction of one revolution can be measured in degrees, gradients, or radians. Now, you're most familiar with degrees. A degree is 1/360th of a revolution. That's why there are 360 degrees in a circle. A gradient is 1/400th of a revolution, and that's a system that is not commonly used. A radian, this we will definitely use. A radian is 1/2π of a revolution. 1/2π of a revolution. All right, so let's look at what a radian is. A radian is defined as that is, 1 radian is the angle you get when the arc length s equals the radius r. This is the definition of a radian. You can think of a radian as a nice pie slice. A nice pie slice is when the crust there, the arc length that I'm kind of tracing out now with the mouse arrow, that would be your crust. And when that crust length equals the radius, that's a very nice pie slice. So think of it that way if you like, or just think of it as S over R equals 1. In any case, theta is always equal to S over R. When S equals R, the theta is, of course, 1 radian. But, S can be smaller than R or bigger than R, and the number of radians would change accordingly. But the basis of the whole radian system of measurement is when the arc length equals the radius. Radian angles are often written without units. And this is interesting because a radian angle is really always a ratio of arc length to radius. And when you write that ratio, you get this. Theta equals, for example, s centimeters over r centimeters. Well, the centimeters cancel, and so you're left with just a pure ratio that has no units because the units have canceled. All right, so sometimes you'll see radian angles written with rad as an abbreviation, but often you'll see them just written without units, like theta equals pi over 6 or theta equals 2.3. Whenever you see an angle written without units, you know that you're dealing with radians. All right, moving on. Let's look at how many radians there are in a full circle, and we can actually just count them. All right, so let's look at this circle here, and we can see that we have more than 6 radians. More than 6 radians. In fact, it looks like about 6 1/4, right around there is how you would probably estimate it. Well, it turns out that there are exactly 2 pi radians in one circle. If you just look at your calculator for a minute and do 2 times pi, see what you get, you'll end up with 6.28 something. And that matches the result that we can count, which is that there are 6.28, about that, 6.28 radians in this circle. All right, so quick review of what pi even means. We're used to using pi, and we've heard of pi, and we know that pi is 3.14159, etc. And it's something that you've been exposed to, but what we often forget is, well, where does pi actually come from? This is where it comes from. Pi is defined as the ratio of circumference to diameter. So every circle, great and small, the tiniest circle, the largest circle, it doesn't matter as long as it's a perfect circle. The ratio of circumference to diameter always equals pi, 3.14159, etc., etc., etc. Circumference divided by diameter always equals pi. Well, rewriting that, we have circumference over 2r because 2 times the radius is the same as that diameter, so that equals pi. And of course, multiplying both sides by 2r, we get that the circumference equals 2 pi r. This is another common geometric formula that we're used to throwing around, but this is where it comes from. Circumference equals 2 pi r. Now what do I mean by circumference? I mean the total way around a circle. Okay, so if I start here where the mouse arrow is pointing now, and I just trace and trace and trace, trace and trace and trace, and trace all around the circle, just keep tracing and tracing. The distance that I'm tracing out is the arc length, which is for a full circle equal to 2 pi r. Now, we know that there are 360 degrees in a circle, and on this diagram here, we can count that there are 2 pi radians in a circle, and therefore 360 degrees equals 2 pi radians. This is how we're going to be able to convert radians to degrees and degrees to radians. So 1 degree equals pi over 180 rad. All right, and you can prove that to yourself just by dividing both sides of this equation by 360, and you get 1 degree equals pi over 180 rad. And likewise, 2 pi radians equals 360 degrees. Therefore, 1 radian equals 180 degrees over pi. Prove that to yourself by dividing both sides of this equation by 2 pi, and you get 1 radian equals 180 degrees over pi. So to convert degrees to radians, you multiply the degree angle by pi over 180 degrees. To convert radians to degrees, multiply the radian angle by 180 degrees over pi. All right, so a quick example of that. Convert 30 degrees to radians. Pause the video, do that on your own, and then resume when you have an answer. Should have gotten this. 30 degrees times pi over 180 degrees equals pi over 6 radians. Convert pi over 2 radians to degrees. Pause the video, do that on your own, and then resume when you have the answer. Pi over 2 times 180 degrees over pi equals 90 degrees. That's the correct answer. Now here's some common radian angles. And after a while, you just start to learn these by memory when you use radians enough. If you've already taken trig and you're in calculus, you've used radians a lot. If you're in trig now and are going to get to radians later, then you'll be using them a lot. But in any case, these are some common radian angles and their equivalents in degrees. So we have theta equals 0, which is just 0 degrees. Theta equals pi over 6, that's 30 degrees. Pi over 4, 45 degrees. Pi over 3, 60. Pi over 2, 90, etc., going around the circle. When you get to theta equals 2 pi, that's just 360 degrees, a full circle, which of course happens to be the exact same thing as 0 degrees, because you end up at the same place in the circle. All right, practice problem. A wheel is rotated so that a point on the edge moves through 1.5 meters. The radius of the wheel is 2.50 meters. It's a pretty big wheel, as you can imagine. You know, if the meter is about 3 feet or so, we're talking about a pretty big wheel. Through what angle in radians is the wheel rotated? Okay, so what's the problem asking for? We have our arc length, S, which is 1.50, and we have our R, which is 2.50. So pause the video, solve this problem, and then resume when you have your answer. Okay, so the solution, we're given S equals 1.50 meters, given R equals 2.50 meters, theta equals S over R, and therefore 1.50 over 2.50 equals 0.600 radians. Now let's talk a little bit more about the arc length S. All right, S equals R theta, and that's the simple consequence of the fact that over here on the upper left, if theta is simply defined as S over R, well then multiplying both sides of that equation by R gives you S equals R theta. And so arc length is simply the radius times the angle. Now this only works, of course, when theta is given in radians. If it's given in degrees, you have to convert to radians first. Here's an example. A pumpkin pie is 30.0 centimeters in diameter. If I cut from the center to the crust and then cut again from the center to the crust at an angle of 60.0 degrees to the first cut, how long will be the crust of the resulting slice? All right, so using S equals R theta, pause the video and then resume when you have your answer. All right, this is what you should have done first, as I said in the last screen. S equals R theta only works when you're using radian angles. So first you have to convert 60 degrees to radians, and you have pi over 3 radians. And now you can use S equals R theta, and we have 15.0 times pi over 3 equals 5 pi centimeters, which is about 15.7 centimeters. Now, if for some reason you didn't put 15.0, this is a good time to kind of address that error and make sure you're always careful. If the problem says 30 centimeters in diameter, well, then you have to divide that by 2 to get the radius. Okay, I'm sure a lot of you did that, but just in case you didn't, and you just put 30 in for R, remember to be careful and read the problem carefully and don't fall into that trap. Now let's talk about angular velocity, also known as rotational velocity.
In this video, we're going to relate tangential and rotational velocity. We're going to begin with a simple demonstration. On the tire, there are two letter E's that are the exact same size, but one of the E's is located at a point near the axis of rotation, whereas the other point is located on the rim, a point that is farther away from the axis of rotation. What you should notice is that the E that is near the axis of rotation is easily recognizable as the letter E, but the E near the rim is blurred. In this video, we're going to talk about why that is. There are two ways to describe the motion of a rotating object. You can talk about the object's rotational velocity, which is how fast the object rotates through a given angle in a given period of time. Now we write that as omega, which is the object's rotational velocity, and that equals the change in the angle, usually expressed in units of radians, divided by the time it takes for that object to rotate through this angle. The other way we can describe the motion of a rotating object is to talk about the object's tangential velocity, which is the velocity of a point on the rotating object. And we write that as a v with a subscript t indicating it's the tangential velocity, and that's going to equal the distance that a point on that rotating object travels through divided by the time it takes for that rotating point to travel through that distance. Now in this video, we're going to talk about the object's rotational velocity, and we're going to talk about the object's tangential velocity, and then we're going to show the relationship between the two quantities. Now the first thing we're going to do is we're going to talk about the object's rotational velocity, which is often called the object's angular velocity, which is again how fast this object rotates through a given angle in a given period of time. Now we said that we can write the object's rotational velocity as the change in the object's angle divided by the time it takes for the object to rotate through this angle. Now as an example, let's suppose this object rotates through some angle. In this case, let's say that the angle through which the object rotates is 45 degrees. Which we can later show that this works out to be pi over 4 radians. If the time it takes for this object to rotate through this angle, this pi over 4 radians, is 2 seconds, then we can calculate the object's angular velocity. And to do that, we'd say that the angle through which this object rotates is pi over 4 radians, sometimes just written as rads, divided by the time it takes to rotate through that angle, which is 2 seconds, and that equals pi over 4 divided by 2, which works out to be 0.39 radians per second. And that's the angular velocity of this object. Now something I'd like to point out is the angular velocity at this point and the angular velocity at this point are identical. Both of these points are rotating through the same angle in the same period of time. And that's true of any point on a rigidly rotating object. So any point on a rigidly rotating object, whether it's this point or this point or this point over here, will all have the same angular velocity because each one of those points is going to rotate through the same angle in the same period of time. Now in the last part of this video, we're going to talk about the tangential velocity of a rotating object. Now the tangential velocity of an object increases the farther you are from the axis of rotation. And that's because a point that is far from the axis of rotation has to travel through a greater distance than a point that is closer to the axis of rotation, even though these two points are rotating at the exact same rate. That is, each one of these points has the exact same angular velocity. They're rotating through the same angle in the same amount of time. But since this point way out here has to travel through a greater distance as this wheel is rotating than a point that is closer to the axis of rotation, this point is going to have to travel faster because it has to cover a greater distance in the same amount of time. Now in the last part of this video, we're going to figure out how to calculate the tangential velocity of a point on a rigidly rotating object. And to do that, we're going to use the arc length formula for a circular object. Now I prefer to write this as delta theta, the angle over which we're considering the length of arc, times the radius, and that's going to equal the distance, the arc length. And to give you an idea of what I'm really calculating, the arc length is this length, this distance between these 2 points. And delta theta is the angle between these 2 lines, these 2 green lines. So one way I want you to think about this is, this is the distance through which a point on the wheel rotates. This is the angle through which this wheel is rotating, and this is the distance from the axis of rotation. Let's just work with delta, which is the distance a particular point on the rotating object travels, and again that's going to equal the radius, which is the point that's going to change, times the angle through which this object rotates. Now the time it takes for this point right here to rotate through this distance is going to be the same amount of time it takes to change that angle. And so we can write that as the time it takes to rotate through this angle is going to equal the time it takes for this point right here to travel through this arc, through this distance. Now one of the things I'm hoping that you see is that this relationship here, this delta s, the change in distance divided by the change in time, is really the definition of velocity. And since this object's rotating, we call this the tangential velocity. And the other thing I'm hoping that you see is this quantity right here, this change in angle divided by the time it takes to rotate through that angle, that's really the object's angular velocity. And so we can write the tangential velocity of this object as v subscript t for the tangential velocity equals the radius, the distance from the axis of rotation, times the object's angular velocity or angular speed. And this relationship will tell us how to calculate the tangential velocity at a particular point on the rotating object.
And now a few cartoons. This wheel is going with an angular velocity of about 1 radian per second. The ladybug is at a radius of about 1 centimeter. Notice how it has a small tangential velocity, that green velocity vector. And it's small because the ladybug is pretty close to the center. Now the ladybug is 2 centimeters away, farther from the center. It has a bigger tangential velocity because the radius has increased, even though the angular velocity is still remaining the same at about 1 radian per second. Now what happens if we increase the radius even more? Well, if it's near the edge, the ladybug has an even bigger tangential velocity. You can see that the green vector is bigger, because the radius is bigger, even though the angular velocity has not changed. This wheel has been spinning at about 1 radian per second the whole time, so angular velocity has remained the same, but the linear velocity has increased. Now it's time for some algebra. So if velocity equals displacement over time, this is something we have been doing all year, just displacement over time, that's the definition of velocity. And if s is an arc length, which is a displacement, it is a displacement around the outer edge of the circle. On a rotating circle, the tangential velocity, v sub t, is arc length over time. So that makes sense. We just have distance over time. So arc length over time. And so v sub t equals s over t. Now that s is our symbol for arc length. We've also been using it all year as a symbol for displacement. And so it makes sense. V sub t equals s over t, displacement over time. All right, now using what we proved in the previous screens, we can replace s with r theta, and so we have v sub t equals r theta over t, which in turn is the same exact thing as r times theta over t. Now we'll see why that's important in just a second. Now, on a rotating circle, the angular velocity, omega, is angular displacement over time. Angular displacement over time. That is how many radians the circle has moved through in a given period of time. So omega equals theta over t. That is the definition of angular velocity, is that omega equals theta radians over t seconds. And now we can see, or we're going to see, why simplifying VT was important earlier, or why we did it up here in this part here where I'm circling, because we can write V sub t as r times theta over t. And notice that theta over t is the same as omega, and therefore we have this formula, which will be very important. So write it down, highlight it, whatever you want to do, but v sub t, the tangential velocity, equals r omega. And you can see that the tangential velocity will be proportionate to the radius. You know, if you have a big radius for a given omega, you're going to have a very large VT. If you have a small radius for the same given omega, you'll have a very small VT. We're going to talk about that a little bit more on the next few slides. All right, so wheels turn angular velocity into tangential velocity. The whole wheel, because it is in contact with the road, moves forward at velocity v sub t. All right, so if my omega shows that I'm going around and around, okay, and I've got a radius r, already proven that v sub t equals r omega, and so we can see at the bottom of the circle, right, the v sub t is going backwards. The top of the circle, the v sub t is going forward, but the whole wheel moves forward at velocity v sub t because when this tire hits the road, it's turning this backward vt into a forward vt of the whole wheel. Let's try this problem. A race car is going around a circular track with a radius of 122 meters at 90.0 kilometers per hour. What is its angular speed in radians per second? Pause the video, do this on your own, and resume when you have your answer. Okay, so now let's go through the solution. We first need to convert 90.0 kilometers per hour to meters per second, and so we do that. And then we use our equation Vt equals r omega. And getting omega by itself gives us Vt over r, and then we just plug and chug, and we end up with 0.205 radians per second. All right, tangential and angular velocity. Let's look at this example. The second hand of a clock is 10.2 centimeters long. Now, by second hand, I mean the hand that measures the seconds. I'm not talking about first, second, third. I'm talking about the second hand, the hand that measures the seconds. Find the angular velocity of the second hand in radians per second. Find the tangential velocity of the second hand's outer tip in centimeters per second. All right, so using the formulas that we just learned, especially Vt equals r omega, pause the video, solve this problem on your own, and then resume when you have your answer. All right, so omega equals 2 pi radians over 60 seconds. Where did this come from? Well, we know in one full revolution, as that hand that measures seconds is going around the clock, it covers 2 pi radians. But we also know that one full revolution of the second hand takes 60 seconds because it's the second hand. It measures seconds. It goes around the clock in 60 seconds. Therefore, we have omega equals 0.105 radians per second. Now, using Vt equals r omega, we plug in our r there, and we have 10.2. Since the problem asks us for centimeters per second, we don't have to convert to meters. Let's leave it like that. And of course, I'm using my unrounded omega since this is just part of the calculation. So you can use the 0.104719551, which rounded to the 0.105. And we're left with 1.07 centimeters per second.
We oftentimes use rotations per unit time to describe circular motion. So RPM, for example, would be revolutions or rotations per 1 minute. And so a lot of times we want to convert RPMs to radians per second. And so here's how we would do that. In this problem, it's saying that the tachometer of your car is reading 1200 RPM. And we want to convert that into radians per second. So here's what a tachometer looks like. And so if we're at 1200, we'd be right about there. And using that unit circle, one complete rotation of a circle would be equal to 2 pi radians. So that'd be one time around. And so to convert our RPM, I'd have 1200 revolutions. I'll just put revolutions here per minute, and I'm going to convert the minutes into seconds. There are, for every 1 minute, going to be 60 seconds, and so the minutes will cancel because they're on opposite sides of the fraction there. And then I can convert the revolutions into radians, and for every revolution there's going to be 2 pi radians, and so the revolutions will cancel and we end up with a speed of 126 radians per second, and so there's our SI units.
Another example, a Ferris wheel with a 50-foot radius rotates at 1.5 revolutions per minute. What is its angular velocity in radians per minute? What is the tangential velocity of a point on the wheel's outer edge in feet per minute? All right, so this is similar to the last problem. Remember that 1 revolution is 2 pi radians. Pause the video, do this one on your own, then resume when you have your answer. All right, so omega equals 1.5 revolutions per minute. We're given that. And then we have 2 pi radians per revolution. That's just something that's a fact. There are always 2 pi radians in 1 revolution. And so when we do this multiplication, of course, the revs cancel, and we're left with radians per minute. So we have 3 pi radians per minute is our omega. Vt equals r omega. Plugging in our givens, we have 50 for r, the 50-foot radius. 3 pi we found for our omega, and so we're left with 150 pi feet per minute. Now we're going to talk about angular acceleration. All right, so just as the acceleration we're used to talking about is an increase in speed over time, well, this is the same. It's an increase in speed, but it's an increase in angular speed. All right, so if we have the average angular acceleration, that's the same as the change in angular velocity over the change in time. Very similar to the way we defined linear acceleration. Okay, it's still change in velocity over time. And just as linear acceleration was meters per second, which was meters per second squared, in an analogous way, angular acceleration is measured in radians per second, or radians per second squared. So angular acceleration refers to changing angular velocities, just as linear acceleration refers to changing linear velocities. All right, the vector nature of rotational motion. The direction of the angular velocity and acceleration vectors is along the axis of rotation. A right-hand roll gives a side. Now, what exactly does this mean? Let's see. If we look at this image here, all right, we can see we've got that wheel. V sub t equals r omega. It has a certain radius. Now, again, this is really just human convention, okay? And since science is a human activity, just as language is, some things depend on human convention and not entirely on logic. But there is some kind of logic to this. Let's look at these 2 vectors, the orange one and the green one. All right, the green vector, omega, is my angular velocity vector. Notice how it's coming straight out of the axis of rotation. The orange vector is my alpha, my angular acceleration vector. And it's also coming straight out of the axis of rotation. Now, for the sake of clarity, we didn't put it right on top of the green vector, just so that you could see both of them clearly. But the actual placing of both vectors is right on the axis of rotation. See these purple arrows? These purple arrows, they're not vectors. They're just kind of showing what the action of this wheel is. They're kind of like cartoon type arrows that show you how something moves. All right, but these purple arrows, this one here and this one over here, these purple arrows are not vectors. So really the only place that is somewhat logical to put the angular velocity vector and the angular acceleration vector is right on the axis of rotation, because if you think about it, it's the axis of rotation where these vectors really take place. Rotation happens along an axis, and therefore it makes sense to put the vectors as having directions along that axis. All right, now a right-hand rule. This is the first time probably you've seen a right-hand rule. You will see it other times in physics. And it's a good idea to understand what we mean. All the right-hand rule is okay, take your right hand out and pretend that you're wrapping your fingers around, making a fist, and that your fingers are curling in the direction of the rotation. Okay, where does the thumb point? It points along the axis of rotation. And so using the right hand rule, you can always tell which way the angular velocity and angular acceleration vector should point. So this is kind of a neat simulation of angular acceleration. Notice how the omega vector, the angular velocity vector, is increasing. Its magnitude is increasing as the disk accelerates. It's turning around faster and faster and faster, and that's why the alpha angular acceleration vector is going straight up in the same direction as the velocity vector. Okay, so it's increasing, 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 and now it's slowing down, slowing down, slowing down. Omega is still pointing up, still following that right-hand rule, but alpha is now pointing down because since it's slowing down, that would be a negative acceleration or a deceleration. And so our alpha is pointing down as the disk moves more slowly, ever so slowly, until it finally stops. Let's talk about the tangential acceleration of a rotating object. We already talked about the angular acceleration of objects rotating more and more rapidly or more and more slowly. Well, now we're talking about the tangential acceleration, and that's really analogous to the tangential velocity. All right, just as you can have tangential velocity, which is remaining constant, you can also have tangential acceleration, which is a change in tangential velocity over time. And just as v sub t equals r omega, in the same way a sub t equals r alpha. And the SI unit, as you would expect for tangential acceleration, is simply meters per second squared, as it is for any type of linear acceleration, meters per second squared. Now, quick proof of why a sub t equals r alpha, just for those of you who like proofs. A sub t is the same as delta vt over delta t, which is the same as delta r omega over delta t because vt is r omega. And that's the same as r delta omega over delta t, which is the same as r delta omega over delta t, and that is simply rewritten as r alpha. Just a quick review of circular motion. So the ladybug is going around and around at constant velocity, and so the tangential velocity, the green vector, remains the same. But the whole time, the centripetal acceleration is directed radially inward towards the center. We did look at centripetal acceleration in Chapter 5, and you remember the acceleration of things that are moving in a circle, like satellites in circular orbit, or cars running around a circular track, or a ball that you're twirling around on a string. And so you have already seen centripetal acceleration, and now this is a new thing, tangential acceleration. Well, let's see how they're different. So a sub t equals r alpha. This is the acceleration that's due to changing angular speed. If you have changing angular speed, well, then that's going to result in a changing tangential speed because the two are directly proportional. Well, centripetal acceleration, which is v sub t squared over r, as you already learned, is due to changing direction of motion. All right, so as we explained in Chapter 5, even though velocity, the tangential velocity might remain constant, there's still a constant acceleration as well that's pointing right into the center of the circular motion. All right, so these are two kinds of acceleration, and most objects that are, moving in a circle will have both kinds of acceleration. Now, of course, if it's moving in a circle at constant speed, the a sub t will be 0. But if the speed is changing at all, then the object moving in a circle will have both an a sub t and an a sub c. All right, now a useful way to rewrite a sub c is this. A sub c equals r omega squared. Remember that vt is just the same as r omega, as we already learned. So we replace v sub t with r omega. Then we square that, we get r squared omega squared over r, and that simplifies to r omega squared. And this is a helpful way to rewrite a sub c. So you should write that down as an equivalent way to write a sub c. This merry-go-round, for example, got some kids on this merry-go-round, and you know how all merry-go-rounds are. They start at rest and then they slowly accelerate. And then, of course, they reach their maximum velocity, which isn't very fast, but they do have tangential acceleration. And they have tangential acceleration precisely because they have angular acceleration. Okay, the angular acceleration results in the tangential acceleration. And as you can see in this example, there's a centripetal acceleration, as there always is with circular motion, and that's our a sub c vector. We also have the tangential acceleration. And the darker purple vector, which would be called the total acceleration, is the resultant of these two components. All right, we're not going to be worrying so much about the total acceleration, but the point of this slide is just to understand that an object moving in a circle can have both an a sub t and an a sub c. All right, here's an example to work through. Mr. Sir, I don't know if you ever saw the movie Holes. It was a Disney movie, and it was Shia LaBeouf's debut. Some of you have seen it, some of you haven't. It really doesn't matter. But anyway, there was this kind of evil dude in the movie, and he was pretty stupid as well. He asked the boys who were in this prison camp to call him Mr. Sir. All right, Mr. Sir twirls a green ball in a circle at the end of a cord. If the ball has a centripetal acceleration of 145 meters per second squared, and the cord has a length of 0.341 meters, what is the angular velocity of the cord? What is the tangential velocity of the ball? All right, so using the formulas that you've learned, you should be able to answer these two questions. Answer them in order. First find the angular velocity and then find the tangential velocity of the ball. Pause the video, do this on your own, and then resume when you have an answer. All right, so the solution, you write down your givens. You have r equals 0.341 meters, a sub c equals 145 meters per second squared. We can use the a sub c equals r omega squared formula. And therefore, we just have 145 equals 0.341 omega squared. And then solving for omega, we get omega equals 20.6 radians per second. Now answering the second part of the question, what is the tangential velocity of the green ball? We simply use the fact that v sub t equals r omega. We plug our answers in, we have 0.341, and then we use the unrounded omega, so 20.6208618, and we end up with a v sub t of 7.03 meters per second. A bicycle wheel has an angular acceleration of 1.5 radians per second squared. If a point on its rim has a tangential acceleration of 48 centimeters per second squared, what is the radius of the wheel? All right, so we know the angular acceleration. That's our orange vector, 1.5 radians per second squared. We don't know the omega, and we don't need to know the omega because the problem is just asking us for r. And we have the tangential acceleration of 48 centimeters per second squared. All right, so you should pause the video, do this on your own, then resume when you have your answer. Here's the solution. Alpha equals 1.5 radians per second squared. That was given. A sub t equals 48 centimeters per second squared. That was given. We use the relationship of a sub t equals r alpha. And therefore r equals a sub t over alpha. And we have our plugging and chugging step. And we end up with 0.32 meters. If you look at this pulley, rope, and mass system, you can see that it's initially at rest. So the omega, or angular velocity, is 0 radians per second. And the tangential velocity is also 0 meters per second. Now, suppose that this whole system is being kept motionless because of some brakes applied to the pulley. Well, what do you think would happen if all of a sudden you released the brakes? You probably already guessed what would happen. The mass would accelerate towards the ground, and the wheel would spin faster and faster. In other words, there would be an angular acceleration. And sure enough, that's what happens. Now let's look at this diagram. Okay, so as we saw in the last section, theta is angular displacement, omega is angular velocity, and alpha is angular acceleration. And as we saw in the last section also, these angular quantities are directly proportional to their corresponding tangential quantities. Okay, so let's look at this diagram on the right, element by element. So we have this pulley rotating clockwise, and as we'll see later, clockwise is always in the negative direction, counterclockwise is always in the positive direction. And so this pulley has an angular velocity and an angular acceleration because of the falling mass. Now I just made up these numbers of negative 2.0 radians per second and negative 1.0 radians per second squared. I just made up those numbers just to illustrate the point. We're not doing any calculation on this slide. All right, so let's see what this means though. This means that the angular displacement is changing by 2 radians per second. In other words, it's rotating through 2 radians per second, and it's negative because it's clockwise. Whereas the alpha, or angular acceleration, is changing by 1 radian per second, or 1 radian per second squared. And that's negative as well because it's clockwise. All right, now if we look at this angle here that I'm kind of outlining with the mouse arrow, we can see that I have the angle theta. This is the angular displacement, and I have the radius, and then I also have this mass that's falling down, and we can see that there has been displacement. There's been a vertical displacement. That's represented by this black vector in the lower right portion of the screen, which is the displacement vector, or S. And as we learned before, S equals R theta. Now, it's kind of the thing I like about this example is that it really shows the relationship between arc length and linear displacement, because as we can see, when the rope is rolled around the pulley, it's an arc, right? It's circular, it's curved, but as it unrolls off the pulley, it becomes linear. And so we clearly see how arc length is linear. The green vector is the tangential velocity, and that equals r omega. The red vector is the tangential acceleration, and that equals r alpha. All right, so this slide is just a quick recap of the last section. Okay, now we're going to get to the good stuff, the equations of rotational kinematics. Now, you'll notice that these equations on the left-hand side of the screen are all familiar old friends. These are your buddies by now, because these were the first real formulas we learned this year, back in chapter 3. And so these formulas on the left are nothing new, but the reason I brought them up is because we're going to see how similar they are to the rotational kinematics formulas. Okay, so for each one of these 5, I'm going to have a really quick proof, and then I'll show the angular counterpart for each of the 5 equations. All right, let's start with the first one. VF equals VI plus AT. Well, remembering what's on the last screen and in the last section, you should remember that the linear velocity, right, is equal to r omega, and so we can simply write this as r omega f equals r omega I plus r alpha t. All we did is we just filled in what we know. We wrote it with the r omega and r alpha formulas that we learned before, because those formulas basically show the relationship between angular quantities and linear quantities. Okay, now those of you who are good at proofs can already see where this is going. All the r's cancel, and you're left with omega f equals omega I plus alpha t. And all this is saying is that the final angular velocity equals the initial angular velocity plus the angular acceleration times the time. Okay, now notice how similar it is, this formula on the right, to the one on the left. Vf equals Vi plus At, omega f equals omega I plus alpha t. Very similar. Okay, let's look at the next formula. Vab equals 1/2 Vi plus Vf. Filling in the angular counterparts, then we have R omega f equals 1/2 R omega I plus R omega f. And again, you can see that all we need to do is cancel the r's and we're left with omega f equals 1/2 omega I plus omega f. Moving on to the third one, s equals 1/2 Vi plus Vft. We have r theta, because s equals r theta, equals 1/2 R omega I plus R omega f t. R's cancel again, and we have theta equals 1/2 omega I plus omega ft. The fourth equation, s equals Vit plus 1/2 At squared. Filling in, we have r theta equals R omega It plus 1/2 R alpha t squared. Canceling the r's, I end up with theta equals omega It plus 1/2 alpha t squared. And all this is saying is that theta, the angular displacement, equals the initial angular velocity times the time, plus 1/2 times the angular acceleration times the time squared. All right, so just as a little bit of challenge, based on the logic of these first four equations, you should be able to show me the angular counterpart of the fifth and last kinematics equation. Pause the video, try to do that on your own, and then resume if you get stuck or when you have the answer. All right, so just filling in our quantities, we have R omega f squared equals R omega I squared plus 2 R alpha R theta. All we did was just plugged in the angular counterparts. And now we do our algebraic rearranging. So we have r squared omega f squared equals r squared omega I squared plus 2r squared alpha theta. And that simplifies to omega f squared equals omega I squared plus 2 alpha theta. And you can see how similar that is to its linear counterpart. All right, so as always with proofs, we only see them once, and then they're in your notes. You can refer to them on your own, but we won't be doing them again. And so to clean all of this up for you, let's just look at the formulas that interest us right now. And so we have the first one, omega f equals omega I plus alpha t. The second one, omega av equals 1/2 omega I plus omega f. The third, theta equals 1/2 omega I plus omega ft. The fourth, theta equals omega it plus 1/2 alpha t squared. And finally, omega f squared equals omega I squared plus 2 alpha theta. All right, let's try this problem. As a cyclist rides along at constant velocity, her bike's wheels spin at 180 revolutions per minute. Upon entering a downhill slope, the wheels accelerate at 20.0 radians per second squared. What will be the angular velocity of the wheels after 10.5 seconds? If the wheel radius is 25.6 centimeters, what will be the bike's linear velocity? All right, I want to give you the sketch for this problem, since that's going to help you to set it up. If we have the girl going down the hill, there's going to be an angular acceleration, and that's indicated by alpha. And we see that down here. Notice that in the first frame and the second frame, alpha is the same because we're dealing with constant angular acceleration. Here I've labeled omega I, the initial angular velocity, and even though this curved line is not it's not a vector, because as I said before in the last video, the direction of the angular acceleration vector and the angular velocity vector is perpendicular to the plane of rotation. It goes along the axis of rotation. But it's much easier to visualize this way. And that's what we're trying to do here, is just visualize. All right, and so we have omega I. And notice how omega I is small in the first frame, but omega F is big because the omega has increased. And notice also that there is a VI, a linear velocity here, just the velocity of the bike and biker together. And the VF in the second frame is bigger in magnitude because there has also been a linear acceleration. Remember that angular acceleration and linear acceleration go hand in hand. So what you need to do is answer the first question first, and don't even worry about the second question until you've answered that. Alright, so what you're going to do is pause the video, do the rest on your own, remembering to do the first part, the first question first, and do it with the same steps as before, where you do the layout and you do the choosing of the equation and then the calculation. Alright, so pause, work on that, and then resume when you get your answer or if you get stuck. Okay, let's go through the solution now. The first thing we want to do is convert the initial angular velocity, or omega I, to radians per second. And so we have 180 revolutions per minute times 2 pi radians per revolution times 1 minute per 60 seconds, and that gives us 6 pi radians per second. Now we're given alpha, which is 20.0 radians per second squared. We're given t, 10.5 seconds, and we need to find the omega f, or the final angular velocity. Now notice I'm not even writing down the radius because I don't need to know the radius for the first question. That's going to come into play when we answer the second question. And I'm doing it this way because I just want to emphasize once again how important it is with these kinds of problems to separate parts. If you mix things up, you get into trouble. So it's a really good habit to just separate and answer one question at a time. Well, with this layout, the choice of equation is obvious. Omega f equals omega I plus alpha t. Now we do our plugging and chugging, and we end up with 229 radians per second. So that is the final angular velocity. And so we can see that going down the slope, the biker's wheels have experienced an angular acceleration, and so the final angular velocity is greater than the initial angular velocity. Alright, now the last question is, what is her linear velocity? Now, recall that a wheel, basically, it transforms angular velocity into linear velocity. Because at the outer edge of a wheel, there's a tangential velocity, and that translates into an overall linear velocity. Now I'm going to quickly go back to the diagram just to explain what I mean by that a little bit more. So I'm just going to go back to the diagram. And here's what I mean by that. Okay, so I'm circling the wheel now with the mouse arrow. You know that there's a spin rate. Well, if there's a spin rate for this wheel, that means there's also a tangential velocity. But notice that the tangent line to the wheel is the ground. The tangent line to the wheel is the ground. And so if the wheel has a certain tangential velocity and it touches the ground, well then, the overall linear velocity of the bike and biker together is going to equal that tangential velocity. Alright, so now let's go back to the calculation. So we have Vt equals r omega, and we do our plugging and chugging there. Notice that I did 0.256 because we just took that 25.6 centimeters and converted it to meters. And also we 228.849556 because that's the unrounded omega f. Whenever you're doing calculations, you use the unrounded, and you round off for your final answers. And so final answer, Vt equals 58.6 meters per second. This means that the overall velocity of bike and biker together will be 58.6 meters per second, precisely because the tangential velocity of the wheel is 58.6 meters per second. Now that we've talked about kinematics, we're going to move on to torque, but before I introduce torque, let's look at something that is, I guess, more common to our everyday experience and makes more sense. And then we'll move on to its related concept, which is torque. So let's talk about balance. We all know what balance is. And this situation here where I have a large mass that's close to the fulcrum or pivot point and a smaller mass that's far from the fulcrum or pivot point, they balance each other. And we intuitively know, anyone who's played on a seesaw or a teeter-totter knows this principle, that if you have a mass far from the pivot, it behaves as a heavy mass that's close to the pivot. All right, and the proportion is simply that m1, or the big mass, times a, the small distance, equals m2, or the small mass, times b, or the big distance. This is also known as the lever principle, which Aristotle first came up with, but Archimedes perfected. All right, let's have a little bit of fun with balance. And a lot of this you've kind of, been exposed to all your life. It's nothing new, but I think it helps to learn the concept if we can visualize it. All right, so we have a 5 kilogram fire extinguisher, two of them, and a 10 kilogram trash can. And we need to put it on this plank, which has a central pivot. And let's do some balancing here. So I'm going to put this guy over here. Obviously it's off balance. 10 kilograms at 1 meter from the pivot point. Well, how can I balance that 10 kilograms? I have a mass that's half of the 10 kilograms with this one fire extinguisher. So why don't I put it here? What happens? That didn't work. Why don't I put it here? What happens? Still didn't work. Why don't I put it here at the 2? Well, that does work. And let's see why. Well, the 5 kilograms times 2 meters, that would be 10 kilogram meters. And of course, if we, multiply the 5 kilograms by 9.81, we would get the appropriate amount of newtons. But we can see that 5 times 2 is 10, and 10 times 1 is 10, and therefore they balance. All right, what would happen if I put this other guy here? Let's say I put him right there. Oh, well, that's off balance. How come? Well, it looks like I have 5 times 2. That's this guy, that would be 10. And I have 5 times 1, that's overall 15. But then over here I have 10 times 1, which is 10. So what do you think I should do to balance it? Well, what do I have to multiply 10 by to get 15? 1.5. So let's put it there, and sure enough, they balance. 10 times 1.5 is 15, and that would be the sum of these two torques here, which would be 5 times 1, which is 5, and 5 times 2, which is 10. So 5 plus 10 is 15, and they balance each other out. Let's check out another activity. Remove the supports here, and we'll show everything. Okay, so this is also fun. I can see what happens, for example, if I put a 20 kilogram weight here at 0.5, and then I put a 5 kilogram here at 2, and they balance. Okay, that's pretty neat, huh? It's kind of fun. It's like playing on a seesaw or teeter-totter, whatever you like to call them. Let's see, what can we do now? Let's put a 10 kilogram weight right here and see what happens. off balance. Well, let's look at how we can balance it. I've got 5 times 2 here, which is 10, plus 10, that's 20. But over here I have 20 times 0.5, that's 10, which means I need another 10. So there are different ways I could do that. Why don't we put the 10 over here, and now I balance out. Okay. Now this is just kind of a quick little demo of something that you intuitively know, which is balance, but it's related to a concept that we're about to see. Center of mass. The center of mass of a system is the point where the system can be balanced in a uniform gravitational field. Alright, so this concept is related to what we've seen in the past few slides, the concept of balance. But what's a little bit different about this is that even though we normally think of the center of mass as what a single object has, 2, 3, 4, or many objects, a system of objects, can have a center of mass. And that is the point at which gravity acts on a mass as if all the mass were concentrated right at that point. Okay, so whenever we draw vectors for masses, usually we draw them from the center of the body. Alright, so the center of mass need not be within the object. Now it often is, as you can imagine, but as we can see with this lifesaver disk on the bottom, it's not always. Now, it's kind of a common sense notion that when you see a disk, you balance it, and you can tell that if you were to locate the center of gravity, you wouldn't pick a certain point within the disk. It just kind of makes sense. And we'll see a handy way to find the center of mass in just a second. But the important thing to remember about center of mass, it's the point at which all the mass of an object acts as if that mass were concentrated right at that point. Okay, so the neat thing about the center of mass as well is that when things are rotating, the center of mass remains stationary. All right, and that kind of further illustrates the fact that with the center of mass, it's as if all the mass were concentrated at that one point. Now, an easy way to find the center of mass of an object, let's suppose we have this map of the United States made of wood. It's a carving, right? And it has a certain mass, but obviously it's an odd shape, and it's not really easy to just pick a random dot in the middle and say that's the center of mass. So the foolproof way to find the center of mass is this method. You simply hang it from one point, trace that line, the vertical line, and then hang it from another point, trace the vertical line, and the two lines meet at the center of mass. And the neat thing too is it really doesn't matter which 2 points you pick. 2 intersecting lines from 2 similar points like this, points of hanging, will intersect at the center of mass.
Let's say we have 2 masses and they're separated from each other by a certain distance. And we know that the center of mass is not going to be right in the middle because the M2 is so much bigger. So how would we find the center of mass? The way we do it is we consider the distance that each mass is away from a reference point. So in this case, M1 is x1 away from that reference point. M2 is x2 away from that reference point, which could be anything. You can choose the reference point. And what matters though is that whatever reference point you choose, the distances between them, or the torques really, because it's just a mass. It's a mass times a distance, so that would give you a torque if you had a force times a distance. But what you do is you just multiply those and then you divide by the total mass of the system, and that's going to tell you which point is going to be your center of mass. So this would also work for more masses than just 2. And the principle just extends. You just keep doing mass times distance plus mass times distance, etc., over the total mass. Now, a quantitative example of this we can see in the next slide. We have let's say we have 4 masses, and let's pretend we're putting them on a number line. So 30 kilograms is at -2 meters, 5 kilograms at 3 meters, 10 kilograms at 6 meters, 15 kilograms at -3 meters. And we want to find the exact point on the number line that would be the center of mass of this system. So the convenient reference point, of course, is the origin itself. Now, notice that the formula, it looks complicated with the symbols, but it's really not. The sigma just means add them all up, because mixi is just m1x1 plus m2x2 plus m3x3 plus m4x4. And as you can see, that matches the formula from the previous slide. So you're just adding all those up. And then you find the total mass of the system. In this case, we're just adding all the masses up. That's 60 kilograms. And then we simply divide the moment of the system by the total mass, and we get -1/2. That means that for this particular system, the center of mass of the system is located 1/2 meter to the left of the origin. 1/2 meter to the left. And you wouldn't know that without the formula. You would maybe have kind of a rough guess of where the center of mass is, but this is the way to find it exactly. Here's the classwork. Please write these numbers down, and we'll post the worksheet. See you in class.